We have been making a promise since the very first episode. We told you a large language model is context-aware, that it can read the sentence after living in Tokyo for 10 years she was completely fluent in, and lean hard toward Japanese. And we said the machinery behind that would get its own episode. We also told you, back when we talked about the context window, that the reason a window is so expensive to grow comes down to one mechanism scaling badly. Both of those promises point to the same place. The single most important idea in modern AI, the one that the entire field is named after, the transformer. And the beating heart of the transformer is a mechanism called attention. Today we take it apart. No heavy math, just the real shape of how it works. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. Start with the problem. Attention exists to solve because it grows directly out of episode 3. We turned each token into an embedding, a point in a space of meaning. But there was a catch we glossed over. A plain embedding is frozen. The word bank gets one fixed vector, no matter what sentence it is in. Yet you and I both know that bank in I sat on the riverbank has nothing to do with bank in I deposited the check at the bank. Same word, completely different meaning, decided entirely by the words around it. A frozen embedding cannot capture that. So we need a step that takes those static vectors and adjusts each one in light of its neighbors, so that the vector for bank actually shifts depending on whether river or check is sitting nearby. That adjusting step is attention. It is how a model turns a word's generic meaning into its meaning right here, in this specific sentence. So here is the whole idea in one sentence. Attention is the mechanism that lets each token look at every other token in the text and decide how much to let each one influence its own meaning. Picture a sentence laid out, every word a person standing in a room. To understand its role, each word turns and looks around at all the others, paying close attention to the few that matter to it and mostly ignoring the rest. Take the classic example. The animal did not cross the street because it was too tired. What does it refer to, the animal or the street? You know instantly it is the animal, because tired only makes sense for a living thing. For the model to get this right, when it processes the word it has to look back across the sentence and pour most of its attention onto the word animal and very little onto street. That act of looking back and weighting what matters is attention, and it happens for every token all at once. Now, how does a word actually decide who to look at? This is the cleverest part, and there is a beautiful analogy for it that comes straight from search. For every token, the model produces 3 different vectors, and the names are worth learning because you will hear them everywhere. A query, a key, and a value. Think of it like dating profiles, or like searching a library. The query is what this token is looking for. The word it sends out a query that effectively says, I am a pronoun. I am hunting for the noun I stand in for. Every other token offers up a key, which advertises what it is. The word animal holds up a key that says, I am a living noun, a good candidate to be referred to. The model compares the query against every key, and where a query and a key match strongly, that is a high attention score. So it sends out one query and checks it against all the keys, and the strong matches light up. Then comes the third vector, the value, which is the actual content the token passes along once it has been chosen. The attention scores become weights, and the token pulls in a blend of everyone's values, mostly the value from animal, a little from the others. The result is a new, updated vector for it that now literally carries the meaning of animal folded into it. That is the magic trick. Words physically mix their meaning into each other in proportion to how much they matter to one another. And the model does not do this just once. It does it many times in parallel, in what is called multi-head attention, and this detail is what gives the mechanism its real power. Imagine not one set of query, key, and value, but a dozen sets running side by side, each its own attention head. Because they are separate, each head can learn to care about a different kind of relationship. One head might track grammar, linking verbs to their subjects. Another might follow pronouns back to the nouns they stand for, exactly our, it, and animal case. Another might watch for tone or for which adjectives modify which nouns. Each head looks at the sentence through its own lens, and then all their findings get combined. So when a token's meaning gets updated, it is updated by many different kinds of relationship at once, woven together. This is a big part of why these models capture language so richly. They are not reading a sentence one way. They are reading it a dozen ways simultaneously. There's one more thing that made the Transformer such an earthquake in 2017, and it is about speed, not just understanding. The systems before it read text strictly one word at a time, left to right, each word waiting for the one before it to finish. Like reading through a straw. That was slow, and it was hard to scale. Attention threw that out. Because every token compares itself against every other token in one big simultaneous operation, the whole sentence can be processed in parallel, all at once. Which is exactly the kind of work the graphics chips we will talk about soon are built to do. That parallelism is what made it possible to train on the entire internet, which is what made the giant models of Episode 1 possible in the first place. The paper that introduced it had a title that has since become famous, almost cocky. Attention is all you need. It turned out they were right. But that same everyone looks at everyone. Design is exactly the cost we warned you about in Episode 4, and now you can see precisely why. If you have 10 tokens, each one looks at all 10, so that is roughly 100 comparisons. Double it to 20 tokens, and now it is 400 comparisons. The work grows with the square of the length. Triple the text, and the work grows about ninefold. This is the quadratic scaling we promised to explain. It is why the context window cannot just be made enormous for free, why long prompts are genuinely expensive to run, and why a whole field of research exists purely to make attention cheaper so the window can grow. The thing that makes the model brilliant at understanding is the very same thing that makes long inputs costly. The strength and the limit are two faces of one mechanism. So how does attention land depending on who you are? As an individual, you almost never touch it directly, but you feel it every single time the model correctly handles a tricky sentence, resolves a confusing pronoun, or keeps track of who did what in a long paragraph. That fluency you take for granted is attention quietly weighing your words. As a startup, you do not implement attention, but understanding it changes how you write prompts. Knowing that every token attends to every other token tells you why a cluttered prompt full of irrelevant text actually hurts, because all that noise is competing for the model's attention and diluting the signal. And it tells you why being clear and well-structured genuinely helps the model focus. And as a large enterprise running models at serious scale, the quadratic cost of attention is a line item. It drives the engineering choices, the hardware budgets, and the active interest in newer, cheaper variants of attention, because at millions of calls over long documents, the difference between brute force attention and an efficient version is real money and real latency. So let us bring it home. Attention is the engine that takes frozen embeddings and brings them to life, letting every token look across the whole text, send out a query, match it against every other token's key, and pull in a weighted blend of their values, so each word's meaning is reshaped by its context. Run that many ways at once with multiple heads, do it in parallel across the whole sentence, and you have the transformer, the design behind every model you use, and the reason a machine knows what it refers to. You also now understand from the inside why the context window has a hard and expensive ceiling. We have finished building up the picture of what a model is and how it thinks. From here, the series turns practical. We have mentioned more than once that you can run one of these models yourself on your own laptop with a free tool called Ollama. In the next episode, we actually do it, and we look honestly at the real trade-offs. Because a model on your own machine is private and free, but it is not the same as the one in the cloud, and it pays to know exactly why. That is the core of it. If this helped, hit like and subscribe. Ring the bell for the next deep dive and tell me in the comments what you want broken down next. Thanks for watching.